Alô? Oh, okay. So we should start pretty soon. Tudo certo aí? Tá rolando já? Tá transmitindo? We are live on YouTube right now. Yeah, that's good. Okay, thank you. And before we start, I just want to make sure that, to be clear, that we are recording and transmitting this presentation, and this is why I'm using a microphone. And I like to just start by thanking I'm very thankful for the presence of this very prestigious evaluation board. I'd like to thank everyone that is present here. And agradecimento especial para o meu pai e minha mãe, que também estão presentes aqui. Okay, so let's start. The presentation is going to follow an order which is similar to the dissertation, pretty much the same structure. And because the work is pretty extensive and I do not have much time, I'm going to have to be pretty quick about some things. But if you have questions, we can come back to that later and discuss in more depth. So, first things first, with the introduction. We're dealing with wireless sensor networks here, which are basically networks that have many sensor nodes sending data to a central node, which is generally more powerful than those sensor nodes. Sometimes it is connected to the internet, and most of the time, the data that is gathered by the nodes are stored in a higher level system, either on the cloud or on a local database. But different wireless sensor networks might have different needs. For instance, you may have a sensor network measuring a large forest, for which you would have a large-scale network with sparse traffic and probably with lots of energy restrictions. You want your nodes to last a long time in these very wild and inaccessible areas. Or you might have a small network, for instance, some industrial equipment being monitored by sensor nodes. And this is a very different network. It is small scale, but perhaps you have more time-critical traffic. You can't lose messages, and you need to deliver those messages much quicker. But in all of those cases, the most important thing about the network is usually the data, not the sensor nodes, but the data. And in most of the time, you want to be able to tell where the measurement happened, when it happened, and you need to be able to interpret the data. If I say 42, for instance, this is not useful information, but 42 degrees Celsius, then is much more useful information. And ideally, you want to have evidence to trust that data in some way. To provide that, of course, you need architectural support, either from the operating system or from the communication protocol, or both. Traditionally, this is done by polying up middleware in your network stack that is very heterogeneous. The layers do not speak to each other, they do not know about each other, and usually you have replication of information. You have functionality in one layer that was being done in some other way in another layer. An alternative is developing an application-oriented protocol with a cross-layer stack in the way that layers know about each other, and you deliver all this information in a more synergistic and optimized way. And this is what the Trustful Space-Time Protocol aims to be. It is a wireless sensor network specific protocol. It is a complete cross layer which goes all the way from the application layer to the hardware. And it has building blocks to provide those functionalities that I mentioned. So we deal with time synchronization, location, medium access control, routing, and security. Of course, this cross layer brings a tight interaction between components, which can lead, if we're not careful, to a very coupled software, a very unmaintainable implementation. So we need a very careful implementation and software design. All these building blocks have been implemented in the past by the group. This is just some of the various works that have been performed at Licia. I myself have worked in security around 2015. And the objectives of the present work. The main objective is to evaluate the performance of TSTP. But in the beginning, TSTP didn't actually exist. So at first, we needed to make it exist so we can evaluate it. And so the first specific objective is to implement the Trustful Space-Time Protocol, both for a real hardware and for a simulator. So we can have many different types of evaluation, a very complete evaluation. Then perform experiments in those two platforms. And ideally, we want to be able to optimize the protocol and propose changes to make it better based on the results of the analysis. This is just some of the technology that is used. C++ programming language, E+3 hardware, and so on, the Omnet++ simulator. And we have mainly 3 real-world deployments in which we check if everything is actually working in the real world. We are sitting in one of them right now. As I mentioned, the room next door is completely controlled by TSCP and other aspects of the building too. And this all ends up in the architecture that I just showed you earlier. Okay, so going on to TSTP design, I'm going to talk about some principles and then each of the components of TSTP very briefly. And my main focus here is going to be on evaluation. So I'm going to be especially quick in these first 2 sections here. Usually on wireless sensor networks, when you receive a reading from a sensor, in the most crude way, you would receive something like that. You receive a data and a network address from which the data came from, an IP address, for instance. But actually what you want is something like this. You want to know what the value is important, but there are many other things that are important. The value itself is not interpretable by itself. What you actually want is usually something like this. You want to know what unit that was in, what is the precision, where the data came from, when the data was generated, and you want to have some evidence to trust the proceedings of the data. And this is what we call smart data. And usually, if you have this here, you can derive all that from the network address itself, right? You can have a system that says, oh, this address belongs to that sensor, which is deployed in some way, which is a temperature sensor, and so on. But if you lose the system, if you lose this knowledge, this very specific knowledge for that system in particular, this does not tell you anything. So what we try to do is, and what we actually do, is express information from the beginning in those terms. So we do not need some external system to parse that. And this is actually pretty attainable. We can use Unix time to represent timestamps in an absolute way, very efficiently. There are ways to represent coordinates. And the International System of Units gives us a way to express units in a very precise way. So those are the main principles of TSTP. And besides expressing information, we want to avoid unnecessary replication of information. So for instance, if my radio has to synchronize to send a message to another radio, perhaps I can leverage this synchronization to implement a higher level time synchronization between the 2 nodes, instead of replicating all this information in a middleware pile. And for the context of this work, trustfulness is going to be security. We are just delivering some security principles. The main architecture of the protocol, it is composed of 6 main components, and they communicate to each other via metadata-enriched network buffers. So the buffer comes from the radio, goes to the MAC, and goes all the way throughout the stack to the application, and so on. And these components do not talk to each other directly. They talk via the buffer. I'm going to go into more detail about that later. And these are just the technology that implement each one of those. So going into each of the components in particular in terms of design, there are many ways to estimate positions based on signal characteristics from one node to the other. For example, the signal strength when you receive a message has a correlation with the distance that the message has traveled. However, radio signals are far from perfect, especially in these cheap devices. So if you just trust the RSSI, you might end up with lots of error in your estimation. So the Hiccups protocol, which was implemented as a master's project many years ago in Alicia, it enriches these types of estimation with a deviation. So when 2 anchor nodes can detect that their estimation is wrong, they can broadcast that information to neighboring nodes, which can use this information to correct their own estimations. and it also adds confidence. So nodes can know that they are estimating their position based on perhaps not very precise information. Time synchronization needs to be done periodically because the clocks, especially in those cheap devices, they will drift apart over time. So even two clocks that were once perfectly synchronized, they will drift apart over time. So if you want the clocks to be synchronized, you have to constantly perform clock synchronization. One way of doing that is if you want to synchronize a clock from the master node to the slave node via network message, you can send a timestamp from one to the other, and if this, if the transmission time of the message is none and it is constant, then the clock synchronization is pretty trivial, right? You just add the transmission time to the timestamp that you receive, and that should be the time that you are right now. But the problem is this is not always easy or even possible to implement. So protocols like PDP, for instance, implement a three-message exchange to determine the round-trip time to the network, and this supports multi-hops and so on. And our proposal, the speculative precision time protocol, can work in a way similar to PDP. However, it can eliminate explicit messages from happening. So it proposes to include timestamps in all messages of the network. So for instance, if node A is sending a message to node B, and this is a data message, not an explicit synchronization message, but if that M1 happens to carry an accurate timestamp, it can be used in just the same way as the sync message here. And so if B later on forwards that message, it can be used to synchronization and so on. So in most cases, we can provide clock synchronization without explicit messages at all. The Mac is pretty much based on RBMac, and its main purpose is to leave radios on just for a fraction of time. So it works by, in the example here, you have node S sending a message, and A, B, and C are receivers. A, B, and C, they check the channel in all of those blue squares here with a constant period between them. Okay, so and the rest of the time the radio is turned off. So if node S wants to send a message, it needs to make sure that there will be receivers to that message. So it sends it with a long preamble, which is proportional to this time here. And so each node can receive this preamble and wake up in time to receive the data. This is data transmission, this is data reception. Later on, there is a contention mechanism. Each node will fire off a timer with which is proportional to the distance to the destination. So the node that is closest to the final destination of the message will wake up first, transmit the message, and the other two will receive that and drop their message because another node already forwarded that. And we do not define link layer destinations for messages. We only have the final destinations, and the node geographically route the message to the destination. And RBMac by itself is a cross-layer protocol because it enables routing too. And we can manipulate this offset here to introduce other metrics. For instance, how much energy do I have left? Maybe I don't want the node that is closest to forward the message, but the node that has the most energy, for instance. And we can do that with this equation here. The security we provide right now is just a pair of keys, symmetric keys between a sensor and a gateway, based on these algorithms as building blocks, and some space-time information. You need to know the exact space-time where the sensor will be deployed to generate that key, and this adds another layer of security. It just works as two Diffie-Hellman messages, and then authentication messages later on. We can come back to that later if you have questions. The Smart Data API is what you saw in the demo earlier. It defines the way that we express units inspired by the standard in the International System of Units. And Smart Data also defines that data needs to be sent with an expiry, which is, in the terms of the network, a deadline. If a packet is in the network and it is expired, I can just drop that packet. And this is application defined. And Smart Data also provides a powerful API for the applications of the wireless sensor network, of the wireless nodes themselves. So now we are moving to the implementation part, which follows pretty much the same order. Going back to the component model, it is implemented as each of these components are observers of the radio. And the radio defines buffers depending on the protocol and the network that is on top of that radio. And the buffers may be optimized. In the case of TSP, it is a simple buffer. It has no fragmentation. It has light control information. But for instance, for IP, you may have a more complex buffer with fragmentation and so on. And this, with static metaprogramming techniques, it's transparent to the application. And these buffers they go through the components in the zero copy way. And so components can communicate to each other by inserting information and reading information from that buffer. And the whole TSTP message is available to all the components alongside the meta information. And just an example, if a buffer goes through and comes from the radio interface, the MAC layer might annotate as metadata the reception time of the message. Then the message goes through to the location and timekeeper. Timekeeper takes note of that reception time to perform its synchronization algorithm. And then security might want to check if the timer received the message is greater than the time that the message is sent, for example. And the message goes on. So this is all zero copy. Message they can see the buffer itself and modify it and insert meta information. This is how the buffer looks like in TSTP. It has the message, many pieces of metadata, and a light control information. I'm not going to go through every message, but the common TSTP header is very important. It goes in every TSTP message that goes through the network. And the most important thing here is information about the node that is currently transmitting this message. So we have its coordinates and its time, and we can, because we have timestamps and spatial localization in every message, we can perform space-time synchronization pretty much passively, just by observing messages in the network. And we also have scaling bits, like I mentioned in the beginning. If you're measuring a large field like a forest, you might want to be able to express maybe thousands of kilometers. But if you are measuring just a room like this one, perhaps 100 meters is good for you. So we can optimize the packet size according to the needs of coordinates. And these are just the most common message types of the protocol. Now, implementation of each of the parts, again, pretty briefly. Position estimation is very simple because there are coordinates in every message. We just get the coordinates alongside the radio correlation of distance, and when we have enough data, we can trilaterate and estimate our own positions. Time synchronization, like I said, if this DTX, the transmission time of the message, is none, it is pretty trivial. And in some cases, you can actually determine that, which is the case of TSTP. If you have a bounded clock accuracy, which we have by the standard that TSTP is based on, the physical layer standard, if you are within one hop, the propagation delay of the message is negligible, it's close to the speed of light. And if you have a bounded and no radio delay, this is the hardest part, I'm going to go back to that later. If you have MAC level timestamping, you have pretty accurate timestamp at the time the message is being sent actually by the radio layer. So you need control, very low level control. And if you have time deterministic software, you can actually determine that. In the experiment section, I'm going to show that we actually do that. But if you have that, you can just use every message that comes through to synchronize your clock. As PTP defines a hierarchy, an implicit hierarchy, you always synchronize your clock when you receive a message that comes from closer to the sink than you are. So synchronization goes all the way towards the sink. And we define a mechanism for if you have a requirement of clock precision in your application, because the clock synchronization is defined by the traffic in the network, we define a period P, which after this period, if you have not received any messages, you can fire off an explicit synchronization message. The menu access control implementation is basically realized with this model here. We have the status, and it is the states are fired off with hardware interrupts. So we have either timer interrupts or radio interrupts, or just a function call from one state to the other. And we have implemented an added feature to the media access control implementation to help solve the hidden node problem, which is not actually solved on RBMac. And this is pretty simple to see, and it's going to sound more superficial than the implementation is, but this is the main idea. If you have A and C, which do not hear each other, but node B is in the middle, if A and C try to send, they're going to always collide. If they send with in the same MAC periods, they're always going to collide. So we introduce a random count-out random component before sending each message, so the nodes can synchronize and get their messages through. And security is because security is the AES implementation. The AES is part of the IEEE 802.15.4 standard, so it is pretty common for these wireless sensor nodes to have security, to have hardware implementations of AES available. And we can use that when it is available with static metaprogramming techniques, no runtime overhead at all. And when they are not available, we provide a basic software implementation of AES to be used. And a library for dealing with big numbers was also necessary and implemented, and it is pretty good for those sensor nodes. Now we come to the main part of the work, which is the evaluation. I'm going to talk very briefly about some tools which I find very useful and nice, just to present you. So we, along the way, a PCAP trace visualization, actually a PCAP trace generation tool was implemented both for EPOS Mode 3 and for the simulation. So on EPOS Mode 3 networks, we can deploy a sniffer node, which listens to traffic without interfering in anything in the network and generate a trace. And then a plugin for Wireshark was developed, so we can open up the trace and see the TSTP packet, see if everything's okay, see if the timings are respected, both on the EPOS Mode 3 platform and the Omnet++. There are some steps to verify the implementation of the Mac. This is a basic example of how it's done. So each time you enter a function of, for example, the content function here, if you are in debugging time, you print a specific character to the screen. So later on, we collect these traces and feed that to a separate C++ implementation of the same automaton, and we can check those execution traces to see if no violation of states and transitions happen in that particular run with the code instrumented, of course. So this is not saying the Mac is correct. This is just saying for that particular run, it didn't implement, it didn't feature any state violations. This is particularly important for EPOS Mode 3, where we can have interrupts preempting one another and perhaps causing an out-of-order execution of the Mac. And it helped to show that our implementation doesn't do that. It did in the beginning, so we solved it, and it's fine. So security protocols is pretty important that they are correct. So we have some unit tests for checking the library for big numbers arithmetic. It basically generates traces like this, which we feed to a separate Python program, which checks the operations to see if everything's correct. So this is randomly generated operations. So here I have A equals that, B equals that, and A plus B equals that. So we perform the operation, give the dump, and then a Python program checks if it was performed correctly. Now for the evaluation itself. This is the code footprint of both of the implementations for Castella and for EPOS. This is all in bytes. So this is the total TSTP implementation. And what is a bypass routing is just a very, very thin an implementation of a routing protocol which does nothing for Castella. So this is basically represents the framework overhead itself. This is a simple implementation of a MAC for comparison. But the main comparison here is with two third-party implementations of AODV, which is a routing-only protocol for sensor networks. And we can see that with all of the features of TSTP, we still achieve in both implementations a code size which is comparable to AODV, which simply implements routing. Now the EPOS Mode 3 experiments. This is how an EPOS Mode 3 looked like. It's a very small device. Some technical information about it. So we started by measuring the overhead of the buffer, the zero copy buffer management and allocation process. On average, to allocate buffer, it takes around 2 microseconds on the EPOS Mode 3 device. And the process of notifying that the radio cycle that I talked about, the process of sending the buffer from one component to the next is also measured, and it represents about 11% of the total processing time of that buffer, along with security protocols and time synchronization protocols and so on. The buffer passing mechanism represents 11% of the time. Now, time synchronization. As I mentioned, it is possible in some cases to determine that DTX, the time delay that messages take from one node to the other. And there is a physical, a hardware introduction of jitter in this process, because the way that 15.4 radios worked, you have a jitter between the time you send a message from one radio hardware containing a timestamp to the time you receive the message in the other node. And so we measure how much was the time and how constant it was. And this is based on experiments by other authors too. And so the experiment is pretty simple. We had 3 EPOS Mode 3 devices. One was sending timestamps with a fixed period, and other 2 receiving. And the plot here is from one node and the other node, the delay between the message getting sent and getting received. So it was about 3.13 microseconds with a very small jitter, 93.5 nanoseconds. So this is hardware imposed limits on clock synchronization. Because we have this jitter, we cannot trust timestamps that are more granular than that. We need to have timestamps with a granularity of at least 100 nanoseconds or even more. So this imposes a hardware limit on clock synchronization, but it is a pretty good limit. We can achieve very high clock synchronization accuracy, like is shown in the following experiments. So this is one EPOS Mode 3 device sending timestamps periodically and 3 others receiving. And this is the clock offset. This is on real EPOS Mode 3 devices, the clock offset detected after the synchronization was done. So for one synchronization every 3 seconds, we achieve sub-microsecond clock synchronization in every EPOS Mode 3. If we increase that, for instance, to 15 seconds, the accuracy gets a little worse, as expected, but it still reaches tens of microseconds. And if your application can tolerate a lower level of clock accuracy, like for instance hundreds of microseconds, we can achieve up to 30 minutes between one synchronization message and the next. So those were the EPOS Mode 3 experiments. So an analytic model was also developed to measure to help validate the implementation. So we have an implementation, a simulation, and an analytic model to check if everything is correct or agrees with one another. And the analytic model is pretty simple. We measure the network as an MM1Q, which basically has a rate of events entering the network and a rate with which the events leave the network. It has many assumptions. This is a very simplistic model. It models the network as a whole as a very homogeneous network, but the usefulness of that is that it takes very few parameters which depict the topology of the network and also the data rate. And as I'm going to show, it is pretty accurate in some cases. So as we enter the simulation experiments, I just want to have a quick recapitulation of the MAC. If you send more microframes, you spend more energy sending each message, but you can sleep for longer between two channel checks. So more microframes means more energy sending and less energy receiving. So what we want to see first is what is the best configuration of microframes. Do I just increase that forever, or do I just use the lowest one, or is there an optimal point? We run experiments in 3 different scenarios. The first one we call the environment monitoring. So it has sparse traffic, many nodes. The sink is right here. I'm not sure if you can see it. So it has a large network with the sink in the middle. Every node is the same, behaves the same way. We want to see which 2 radio power characteristics are better. So lower radio power means less energy to send the same amount of information. However, you have a shorter radio range, so maybe you have more hops until you reach the destination. And conversely, for a higher TX power. And we also change the data period. So in this case, each sensor node is going to generate 1 data point every 1 minute, and in this case here, every 15 minutes. So in this case, for every time period configuration, except for 60 seconds, the network could achieve 100% delivery ratio. And what happened in the 60 seconds? 60 seconds, it's 1 message every minute per node. So it is the highest traffic scenario. We see that if we start growing the preamble too much, suddenly it takes more time to send each message, and the message have a higher chance of colliding with one another because they are occupying the channel for more time. And so as we see, there is a point where the delivery ratio starts dropping. The analytic model in this case was able to predict that such a point would come. However, it was very optimistic on what the point would be. And one note here, the analytic model only works for when the network is not saturated, because the model itself cannot deal with arrival rates greater than the rate with which you serve messages. Same thing for mean latency. In the point of where the network starts being saturated, we can see an explosion on the mean latency because there are messages all along the way which are basically jamming the channel, so no messages can get through. Again, the analytic model predicted that, but was pretty optimistic. However, when the network is not saturated, this is the same experiment, but without the black lines, without the 60-second lines. When the network is not saturated, the latency has a more linear behavior, and the analytic model was very much more accurate than when the network was close to saturation. And the mean latency is pretty modest, about 1 second or less for a pretty large network. And the question that I wanted to answer was, what is that optimal point of number of microframes? In the network lifetime analysis, we can see that there is actually an optimal point, and it depends on the traffic that goes through the network. If you start increasing your preamble too much, you spend more energy sending messages, and less energy receiving messages, right? So if you have too short of a preamble, you spend too much energy trying to receive messages that are not there. So we spend a lot of energy. But if you have a too high preamble, suddenly your transmitting nodes spend lots of energy trying to send messages. And so the optimal point is dependent on the traffic itself, and the analytic model was, again, pretty accurate. Again, optimistic too in most cases, but rather accurate for the simple model. Those are the best configurations that were identified in the scenarios. Note that we always preferred the higher transmission power because it spends more energy to send the same amount of information, but it shortens the distance because the radio can reach longer. Delivery ratio 100% for all cases. Network life from 30 days to about 260 days. And we were able to reach an effective duty cycle of lower than 1% for the higher periods. Oh, and this considers that every sensor node has only this amount of energy, which is roughly 2 AA batteries, so a pretty limited energy supply. Now, the second scenario, we will repeat those experiments to other two scenarios. The second one is Licia Office. We call it that because it resembles the deployment that we actually have at Licia. And so it has a very smaller field, about 5 by 6. The sync node is over here. So we have we have less nodes than the other experiments. And the nodes are not homogeneous. Some nodes we generate data every 300 milliseconds, which is a pretty short period, and some nodes we generate data every 1 minute. Some nodes are battery powered, and the nodes that are battery powered only transmit messages that they themselves generate. This is to save energy on the nodes that need it the most. And in this case, we keep the same data period generation for every scenario, but we still vary the microframe count and the radio transmission power to see which configuration is the best. Again, there is a point where the network starts saturating at around 55 microframes, and the analytic model got pretty close to that in this case. So this is for different radio transmission powers. You can see that the radio transmission power in this case do not change much on the result because the nodes are close to one another, so it doesn't make a big difference. The mean latency, again the same way. Note that in this case it does not show that explosive behavior that the analytic model suggests. And this is because messages do not have a same expiration time. So some messages will spend 300 milliseconds, not get delivered, and be dropped. The analytic model does not model dropping of messages, and neither different periods per message. And so we can see a pretty linear latency. Again, there is an optimal point in network lifetime, but it is beyond the point where I can still deliver 100% of messages, so we use a shorter one. And so now we investigate a more granular step on the number of microframes and do more repetitions on each experiment to identify the best configuration. So at around 21 microframes, we reach a high delivery ratio with a still higher network lifetime. And this is the network lifetime. We reach about 40 days of operation. The SSB office is where we are in right now. We are actually right here, and this is the network in the other room. So it's pretty much the same experiments, but with more nodes. The same experiment I just saw in the Licia scenario. In this case, the analytic model showed that the network was saturated from the beginning. This is a very high data period for the network. And we can see that we never actually reach 100% of delivery ratio. even in the more granular approach, but we get pretty close. And again, network lifetime with an optimal point, which is beyond the delivery ratio point. And these are the best configurations. Again, 7 dBm of TX power, network time for 15 days to 40 days, still pretty good delivery ratio, but in this case, it is a very high traffic for TSTP, and the network is saturated. And the last set of simulations wants to see how is the time synchronization works. So we use the same configurations, the optimal MAC configurations that we found in the previous experiments, and we vary the synchronization period. What we want to answer is it worth it to pigtail timestamps in every data message? Because you make the messages longer, so you spend more energy to send one message. However, you save explicit messages. So is this always good? Is there a trade-off? So how does it work? And this is what we are trying to show. And we compare that with an explicit version of TSTP, which does not include timestamps, but sends explicit synchronization messages, and a theoretical algorithm, which is basically one synchronization per node per p/2 time. So this would be kind of how the best possible synchronization algorithm could behave, close to that. And so, as we, on the Alicia scenario, as we increase the synchronization period, less messages are generated, less synchronization messages, and the delivery ratio goes up a little bit, but there's not a big difference between the speculative and the explicit approach. The same behavior is observed in latency, but in an inverse way. This is the number of explicit synchronization messages that were sent. The green line here represents the theoretical approach, one message per node per p/2 time. The explicit approach showed a higher number of explicit messages. This is expected because, again, in the Alicia, the network is close to being saturated. So the network actually generates more messages than it should in a theoretical way. And the speculative approach sends less messages. The average clock error is, again, pretty much similar between the speculative and explicit approaches because we are achieving a high level of accuracy. This is the energy gain compared to the theoretical approach. So if you are above 0, you spend less energy, and below 0, you spend more energy. And a speculative approach could save lots of energy when the synchronization period is lower. But if we compare to the actual implementation measured on a real network of the explicit approach, we can see that the speculative one is clearly better in terms of energy. So pretty much the same delivery ratio, pretty much the same latency, pretty much the same clock synchronization accuracy, but a much better energy efficiency, even compared with the theoretical approach in most cases. Same results for one case of the environment monitoring scenario. In this case, it was always 100% delivery ratio. The network is not very saturated. On the left here, you see small synchronization periods, and to the right, larger synchronization periods. These are the continuation. One image is the continuation of the other. Again, latency goes down as synchronization period goes up, and the speculative approach, we can say that it is a little bit better than the explicit one. The number of messages compared to the theoretical, in this case, the explicit approach gets close to the theoretical because the network is not saturated, is more homogeneous, so it actually behaves closer to what it should be in the perfect case. And again, the speculative approach sends much less messages as expected. Average clock error accuracy, the speculative approach and explicit behave pretty much the same way for low periods. However, the explicit approach, its synchronization accuracy is necessarily proportional to the synchronization period. So if you have a too large synchronization period, suddenly you have a very large accuracy. While the speculative approach can leverage data messages that are going through with a higher rate to keep a high, an upper bound on the accuracy. And comparing the energy gain, speculative approach seems to be much better, even compared to the theoretical, and the explicit approach is close to the theoretical. And this is reflected in the measurements of estimated network lifetime. And I should mention there is a point when the synchronization period is too large, where the explicit messages are very few compared to regular data messages. So in this point, the explicit approach starts being a little bit better in energy consumption. However, I want to remember that this comes with a huge cost of clock error. So maybe this is not even a usable case. Now the conclusions. The objectives that we have chosen were all completed. We have implementations for the EPOS platform. We have documentation and overhead analysis. We have more than 3 deployments which are working in the real world with this technology. The performance evaluations were performed on all of the metrics that we chose. And there were some optimizations, some changes proposed to the protocol. What you see in the dissertation is the final product, but there were many things that were tweaked along the way to get to that, and I'm sure Gustavo knows a lot about that. He helped with the implementation too. The contribution and evidence that pigtailing space-time synchronization messages to every message can be effective, as we've shown. The open source TSTP implementations, the documentation, the tools, the analytic model, the simulator, and so on, the Wireshark plugin, and UFSC's IoT infrastructure, which is enabled by TSTP that I showed you earlier. Thank you very much. I'm open to questions now.